Down. Okay, so let me settle some important admin matters first. So last week you had your first lab. Last week you had your first lab, which is your introduction. So this lab 1 here is done. If you look at our schedule, you will see that the remaining labs are all split into 2 weeks. Okay, all are split into 2 weeks. Okay, so lab 3, because of the recess week, is split across the recess week, and so on. Okay, so this is the current plan. In terms of assessment, okay, what you need to do, that's very important. You will be required to submit, okay, a lab report, okay, at the end of the second session for each lab. Okay, at the end of the second session for each lab, you are required to submit a lab report. The template is already provided. Okay, a template is provided. You just need to fill in those questions, answer the questions, either with the code or schematic or whatever you ask you to do. Okay, so important, the second session of each lab is submission plus demo. Okay, so the TA will go around and ask you to demo certain functionality, and you ask some questions, and that will be part of the grade. Then the report that is submitted will be part of the grade. Okay, so important, I repeat, the second session of every lab from now on will be graded. Okay, so at the end of the second session, you must do a demo, which forms part of the marks, plus you will be required to do a submission. The submission deadline will be the Friday of the week, not on the day itself, so you have a bit more time. Okay, so all of your labs are on Wednesday. So the submission folder will close on Friday midnight. Okay, so you have 2 more days to finish up the report before you submit. Can? So I already say now, so later don't say that I did not know, I was not informed. It's also written in the lab sheet. Okay, so in your lab 1, basically what you did is you got the whole installation of your Eclipse IDE install, plus you integrated. So you did 2 things, correct? So the first step, what you did is you integrated your entire library Arduino, correct, into your new Eclipse IDE environment. And what does that give you? It gives you the ability to now code inside a different development environment tool, okay, instead of your normal Arduino IDE. Okay, so that is the first thing. And the second most important thing is you now have the ability to write code directly manipulating registers at the microcontroller level. Okay, so instead of just relying solely on Arduino functions, though they are very good, they are very helpful, they help you to get a very quick start on things. Without understanding too much detail, you can very quickly do an A to D operation, do a PWM signal, and so on. So that is good, but you still want to have a deeper understanding. Okay, so that is the focus of the lab. So the lab exercises are also given to you up front. The Sparks Fun kit also you have. Okay, so if you actually work on your lab exercises before you come to the lab, your lab is also easier for you. You can just come, you can demo, and you can leave, no problem. Okay, so I repeat, if you do your work before the lab, you come to the lab, you just tell the TA, I've already done everything, I want to demo, you demo. And then you can leave. Okay, so it's up to you. You want to spend the 2 hours there to do it, or you want to do earlier, also up to you. Okay, as long as you do the demo on the second session. Okay, okay. So today we are going to start off this chapter, real-time software architecture. and we will also start the next chapter a bit. Okay, so this set of slides is quite short, and then we will start the next set of slides. Okay, so we are still building up some case to understand a bit more of the different options we have. Okay, so this is important because we have your single threaded. Okay, they all need to settle down. Too much of. It's okay to talk. If you want to talk, you can go outside, no problem. Okay, but when you talk in the lecture theatre, it's very disrupting. See, when I'm talking, still they're talking. Can? Finish talking already? Can? You want more time or not? Can I stop for a while? Okay, so the objective, okay, again, is to understand the progression. We know we can do single-threaded programming. Okay, just a while loop, we can write a code, blink LEDs, control sensors, everything. And then now we suddenly say we throw in RTOS. But what is the in-between, correct? So you must also understand that there are options. We don't just want to throw you a RTOS and say, okay, this thing is good for simple program. When your program gets complex, you go to RTOS. Then you think that there is no other option in between. There are options in between. Okay, so we're going to explore some of these options first. So why is this important? Again, when you want to integrate the OS into your system, there's a lot of work involved. Okay? If you do not think that your program is going to go so complex, okay, just a bit of complexity, but it's not going to be so complex that you need the OS, then you may think that effort is not necessary. So you may want to take one of these intermediate solutions for your project. Okay, so let's get started. Okay, most important thing is we are always trying to trade off. Okay, we are always trying to do a trade-off between time and space. Okay, so in our trade-off, okay, in most cases we always say we are trading space and time. Okay, time we know. What is time? Time is your computation time, correct? Okay, if I run a particular algorithm, it takes a certain number of seconds. Then the same algorithm I can code in two sides. So I have maybe, okay, the same algorithm. Okay, I can code in approach A and approach B. Okay, both can achieve the same outcome. Then which one will I choose? Okay, if you are not doing any analysis, as long as you are focused on the output only, then either one is fine. Okay, but if you want to do some analysis, then you will look at space and time trade-off. So what is space and time trade-off? You will say, okay, if I compile with A, how much memory does it take? That is your space. Alright? So the same code that I write, I know I achieved the objective. But if I compile with A code, I consume maybe 32 kilobyte of memory. If I compile with B code, I take 56 kilobyte. Okay, so there's a trade-off of some memory that I'm going to use, okay, for either algorithm. Then is also the time. So one thing is memory, that is the space. The other thing is the time. So how many seconds? So how many nanosecond difference is it going to be if I execute either one algorithm? Again, this trade-off may or may not be significant, again, for your simple projects. When you're writing a simple code, basic functionality, this trade-off may not seem so significant because your microcontroller may have more than enough memory and you don't have so much of restriction in terms of time. But when your system gets more and more complex, then even a small difference between choosing one algo and another algo may decide between whether the system can respond in time or not. So these are the alternatives to the real-time OS. Okay, so we're going to explore these 4 alternatives here and see what are they and how does it actually work and in which way it sort of helps us to grow the code base while the complexity of the system is also growing. So the first one is what we are always familiar with, a simple pole loop, where you have an infinite loop, okay, that goes on forever. And what you try to do, you try to check for a certain event. So when you say check for flag, you're actually trying to check whether some event happens. Okay, event is a general term, correct? The event could be somebody press a switch. It could be some data suddenly come in on your serial port, okay, or somebody send you information over the Wi-Fi. Okay, so as long as something happened, then you go and process the data. Okay, so if the event happened, you process the data, and then you set the flag, clear the flag. Okay, and then you wait in your infinite loop forever. And this may repeat itself n times. Correct? You may repeat this whole thing n times depending on how many tasks you have to cater for. Alright, because every task will trigger some event. Okay, so while you are moving your robot, for example, then you will say, okay, my encoder from my wheel disk is going to come in. But at the same time, a message on the Bluetooth channel may come in. So I just have a loop and I keep checking which one happened. Okay, as long as any event trigger, then I go and cater for that particular event. So this is a simple pole loop. There is also the option of having a delay. Why you want a delay? Basically to handle the cases of what we saw earlier, which is your contact bounce. Okay, so if, for example, I am connecting it to a switch, then I know that when my switch is pressed, I may want to capture the event, but it will also trigger, okay, multiple events like this before it settles down. You must imagine that your processor is always running much faster than all these mechanical transitions. Okay, so this whole code here may actually execute within this time frame itself before the bounce can settle down. So if I do not cater for that inside my code, I capture the first trigger, go and do the code, then the false trigger also I go and do the code again. Okay, so your code is going to run very fast. So within the time frame of those mechanical transition, you may already finish what you're supposed to do. Okay, then those remaining transitions will be all false triggers. Okay, and your code will still go and execute. So to prevent that, with the moment you come in, you must also put in a pause. Okay, and this number that you put in is, there is no magic formula. You can do analysis, you can capture the waveform using oscilloscope and then figure out what is the average time and then put the number there. Okay, so there's no magic formula to it. It's a matter of trial and error to figure out how much time your actual mechanical device takes to settle down. So what is the main plus and minus of this? It works well if you are dedicated, okay, to handling I/O, okay, and when overlapping of events is not so possible. Okay. Why? Because if I have overlapping events, then when the next event trigger, I may not be able to capture it. Okay, the next event trigger may not be able to capture it. Okay, so for example, if I have this situation where I have one section here where I check for the button press, okay, and the other section here is to check for my maybe Bluetooth signal. And if my Bluetooth event trigger and I'm in this code, okay, and while I'm in between this code, a button press happened. Okay, if this check here is only trying to check whenever my button value goes to low, okay, it could miss the entire button press altogether, because when the person press the button, the signal go low, he transition for a while, and then once you release the button, it will go up, correct? So in most cases, your button is when I press, I activate, and when I release, it go back to the reset default state. So if this time period, correct, can be very short, okay, and if this takes n seconds, okay, and if this whole transit code here for my Bluetooth module takes n plus plus something, correct? So if this event happened at the beginning of the Bluetooth code, then very likely I will miss it anyway, correct? Okay, so it all depends on when this event happens. So if I happen that this switch come in towards the end of my Bluetooth code, then maybe when I look back to my button, I may still capture it, correct? Okay, but if it happen at the start here, then by the time I reach halfway through, the fella release the button already. Okay, so the whole event will be lost. Okay, so when there are overlapping events, it's a bit more risky to have this approach. Okay, it may work, it may not work. And of course, it will always most likely fail in event bursts. Event bursts are again events that happens within a very short period of time and then it disappears. Okay, so you may not be able to capture it. And most importantly, it wastes a lot of your resources. Okay, waste a lot of resources because when you're polling for events, you really are just waiting for the thing to happen and then you're not doing anything else useful. Okay, so it's a waste of your CPU resource. Okay, so that is the, again, very typical way we normally code for a microcontroller, because as long as all the objectives are met, okay, I can move my system, my robot is moving, my motor is moving, my sensors are working, the data is in, and the output is expected, then we are very happy with this approach. Okay? Like I said before at the start, the RTOS is a very, very good and powerful option, but you may not need the option. Okay? There is no necessity for you to load an RTOS onto a microcontroller if you don't really need it. Okay? So it's just like, you know, you're buying for your, maybe your great-grandmother one Samsung Note 8 Plus, whatever, and then she just call an SMS, never even on the data. Correct? It's total waste, correct? So you may have the most powerful resources, but if you do not need to use it, then you don't really need to invest in it. Okay, so let's come to the next possible option, which is your round robin. So round robin is again an extension of the previous one. So this task one is basically that whole infinite for loop that we saw just now. Okay? So inside this last one, it will be, sorry, not infinite for loop, but you're basically trying to check if something happened here. The event trigger, and then you do something. So you continuously try to check for different events. Okay, so task 1 could be for the button 1. Okay, then task 2 could be for motor, and so on. So each task is run. Of course, when you run the task code, doesn't mean you're actually going to do something. Maybe you're just going to check if I need to do something. Okay, so you must be able to write your task very short and very concise. Because if any of these tasks you write very long, then by the time you finish that one task and you try to go to the rest of the tasks, you would have missed a lot of possible events. Okay, so each task should be as short as possible. Okay, so again, this approach works if you have enough time between the tasks and you're not necessarily dealing with data that may come in very, very frequently. Okay, because again, n tasks could be any number here. Could be 10, could be 20. Okay, the more it grows, the more time it will take from the task 1 all the way to the end before it can look back. Okay, and if task 1 is supposed to handle the button, if the button comes anywhere after task 1, then I will definitely miss it. Correct? Until I move back to my task 1. Okay, so of course, one possible alternative while using this is to multiply the number of times a critical task needs attention. Okay, so in this case, for example, task 2 is a bit more important. It needs to run a bit more frequently. So within that same loop, I call it 2 times or 3 times. So the delay between one call and the next call is slightly shorter than the period of the whole loop. Okay, so that is one way to get around this. Okay, so I have n tasks here. If I just call one task one at a time, then after I call, I need to wait for the complete period of all the tasks before I can call it again. Okay? And if I want to have a bit more higher frequency for any of the tasks, then I repeat that call inside the main while loop. Okay, so if task 2 is more important, I call task 2 a few more times. Okay, so that can help me to, in a sense, capture or increase the chances of capturing the event when it happens. Okay, within a shorter frequency. So, in terms of strengths, that works well when the frequency of servicing is about the same. Okay, and all tasks are short. The critical element here is, very importantly, that there are no time requirements. Because once there are time requirements, you cannot guarantee it here. Even if I call task 2 twice, here and here, there is still no guarantee that I will definitely capture task 2 or the event for task 2. I can still miss it. Okay, until it go back one more time and maybe I capture it, depending on what it is tied to. So there is still no timing requirement guarantee yet. Okay, so if a device requires less attention in less time, okay, then it takes for the entire loop. So if I have a while loop that takes maybe 50 nanoseconds, okay, to complete the whole while loop, and inside this whole while loop, I got task 1, task 2, task 3, task 4, and task 5. Okay, and task 1, if it needs to be handled every 10 or every 20 nanoseconds, then this is not going to work. Okay, if I want task 1, okay, to be handled maybe every 20 nanoseconds, then it's not going to work. So the only way is what? That means I must keep calling task 1 again and again a few times. Alright? But if I do that, then what happens? Then the rest of it, there's an effect. That means the delay between task 2 and task 3 is going to be longer. Correct? Between task 3 and task 4 is going to get longer. Okay, so you can see that once I bring in the constraint of time, it becomes very, very difficult in a situation like this, where you're trying to insert at which point to call the function and how many times to call the function. Because you make one change, there's a spillover effect to everything else. Okay, and all the previous assumptions that you thought, okay, now it works, but now I got a new function or a new timing requirement, it doesn't work. Okay, so even if we add just one more task, one more device, okay, the whole system can get messed up. Okay, so that is the whole challenge in a simple system. Okay, so the alternative is round robin with interrupts. Okay, so interrupts we saw last week, okay, and the whole idea of interrupt is what? The ability for the microcontroller to, in parallel, while your code is running, the microcontroller in parallel can detect interrupts. Of course, there are a wide range of interrupts. Okay, so what you are going to do in the lab is your GPIO interrupt. Okay, so in your lab, you're going to be connecting a switch. Okay, I can't remember active high or low, and you're going to write an interrupt service routine for it. So whenever I press the switch, I will jump to the interrupt service routine. And of course, this is an external interrupt. You can also have internal interrupts, which are peripherals within the microcontroller. Things like your timer, okay, your serial port, your ADC, okay, a PWM. So all these are your internal peripheral blocks of your microcontroller. And these blocks can also generate interrupts for you. So coming back to this, when a sensor has data to send, you can use an interrupt to trigger. So the device, when it's connected to the microcontroller and we set up the whole interrupt vector table, everything is set, the interrupt service routine is set. So when the device or the sensor wants to send data, it can send an interrupt signal. So once it sends the interrupt signal, what will happen? Your code, the code that you're running, so this is your main code here, your main loop. So your main loop is written okay, such that it goes back. Okay, and anytime when there is an interrupt, you jump to ISR, finish everything, and go back to carry on. So when your sensor trigger an interrupt or generate an interrupt, your microcontroller will jump to the interrupt service routine to handle the processing, and then jump back to the main code to carry on. So the ISR is used for time critical processing. Your sensor is a time critical device, correct? When your sensor sends an interrupt means it wants to send something important to the microcontroller. You do not want to delay it and then lose the information. So once the interrupt is triggered, you immediately jump to the ISR to handle it, and then you go back. So a typical structure will look something like this. So inside your while loop, you do not check for the event to occur. You do not check for the event to occur. You let the event occur and trigger the respective ISR. ISR A could be tied to your button. Your ISR B could be tied to your sensor. So your devices, your peripherals are configured to generate interrupt service routine. So generate interrupt to your microcontroller. So when the interrupt is triggered, what will happen? If this is my whole while loop, this check and this check both will return false by default. So your while loop effectively is not going to do anything until some event occurs and I jump to my interrupt service routine. When the event occurs, I will either jump to ISR A or ISR B, depending on which event that triggered the ISR. And once I jump to interrupt service routine, I do what I'm supposed to do, and then I set the flag. So only when the flag is set in the ISR, inside my while loop, either one of it will transition to true. This transitioning of the flag only happens in the interrupt service routine. So why do I still want to have a flag here and ask my task, call my task A others over here? Why don't I just call this task A others here itself? Because it's still related to task A, correct? And since my sensor already triggered and I'm inside the interrupt service routine for task A, why don't I just do the task A others as well? Because the whole idea of interrupt is what? Is for time critical processing. You do not want to waste too much time in the interrupt and then potentially miss other interrupt. Okay? So what you want to do in the interrupt service routine is only do, here they put do some stuff, but it is more on do the very important stuff. That means what is really important at this point of time. The important thing is what? The data that is coming in, the information that is coming in, I must capture first. Correct? The processing of the data can be done later. Okay? The data is important. The processing is always can be done later. So the very important thing that I need to do inside the interrupt service routine is to capture the data. So if there is an interrupt because there's a serial port data coming in, or interrupt because somebody pressed the button, what am I supposed to do? What is the most important thing that I need to do to prevent loss of data, loss of information? So let me do that important activity first inside the interrupt service routine, and the other things. Okay, the other things I can do later in a function. Okay, so when I do it this way, once I do the important stuff and I come back to task A others. So task A others is also a function. Okay, can be a long function, can be a short function. But since it's another normal function, while I'm doing task A others, I may also jump to interrupt B. Correct? Because B can get triggered. Okay, so by doing it this way, I have higher chances of capturing the interrupts and not missing out. Okay, as long as I keep my ISR short and focus on the critical task ahead. So once I come back here and I execute task A others, while I'm executing task A others, another interrupt may be triggered by the system. So this is the idea behind round robin with interrupts. So the same concept as before, except that now I will let interrupts trigger and let my main while loop in the application handle the details. Of course, your while loop can still have other tasks. It doesn't have to be all flags only, correct? Okay, so inside my main function here, I can also have your normal, maybe function C, then function D. Okay, I can still have normal function call inside my whole while loop. Okay, and let it run as per normal. So this function C and function D may be functions that are not necessarily critical or need to be responsive in any way. So even if I have interrupt, even if I have other things, they are not tied to them necessarily. Okay, so that is the whole idea behind this round robin with interrupts. So the advantage of this is you get immediate attention, okay, for your device. Compared to the previous round robin, okay, where you are going task by task, okay, for a critical event like a sensor trying to send you information, you can still miss it, okay, no matter how many times you try to keep calling. So the advantage with this is you have more, you have the ability to attend to interrupts much more quickly. Okay, but what is the downside to it? You are still taking a while for the data to be actually processed. Okay, so if sensor 1 takes 4 nanoseconds to process, then sensor 2 won't be processed for these 4 nanoseconds. Okay, especially you have a higher priority sensor. Okay, so what does this mean? That means in a situation where this is sensor A and sensor B. Okay, so now we assume that this is, okay, sensor A and sensor B. So sensor A gets triggered first. Okay, I jump to the interrupt service routine, I do some important stuff, and then I set the flag. So after I set the flag, I call task A others. And while I'm doing task A others, I get triggered by sensor B. So when sensor B triggers, what will sensor B do? It will also capture the important stuff and set the flag B. Correct? But it will not process the additional stuff for flag B until I finish the rest of my task A others. Correct? Okay, it will still not process the rest. So I still need to sort of wait. Okay? Then of course there are other complications as to how to handle situation where both sensor A and sensor B may be triggered at the same time. So there's also the concept of priority, correct? Okay, who should be given higher priority if multiple devices all request for attention at the same time? Okay, so now that leads us to again more challenges. So we are trying to make the system as robust as we can, but each step we take, there are still issues that we need to deal with. Okay, and another option is this called function queue scheduling. So in function queue scheduling, the whole idea is the same as what we saw just now, round robin with interrupt. But the only difference is what? The only difference is, okay, you do not, after you do the important stuff. So the important thing to remember is your interrupt service routine must still capture the important critical information first. Okay, so you will still need to do those important, whatever that is important, you still need to do it. Okay, capturing of data, saving the data onto some buffer, that critical, time critical management you still need to do inside the ISR. But after that, what do? I do not set any flag. Okay, I enqueue what is called a function pointer. Have you all studied function pointer? Huh? Some say yes, some say no. Okay, so if you have studied, no problem. If you haven't studied, you will get a chance to do in the lab. Okay, so don't worry. So in a function pointer, basically what you are doing is you are passing a pointer to a function. And you know pointer, normal pointers, correct? You point to variables, most cases. But a function pointer basically points to a function. The advantage of a function pointer is now I can pass this function pointer around and tell myself which function to point to. Okay? So what I will do in this whole approach is I will put into a queue the function pointer, or the address of the function that I want to execute. And inside my while one loop here, all I need to do is, if the queue is empty, then I just wait. Okay? If the queue is empty, that means no event has triggered me yet. But the moment somebody triggers me, that means somebody is in the queue. What I need to do is I use a function pointer to dequeue and then execute the function. Okay, so this is the dequeue and then I execute. Okay, so what is the advantage of this? The advantage of this is in a situation where you have a lot of events. Okay, so let's look at this. I have event A, event B, event C. Okay, and if I look at the priority, I say this is 1, 2, and 3. This means the highest priority. This is the lowest priority. Okay, so imagine this scenario. I got 3 events A, B, C. Okay, A is the highest priority, C is the lowest priority, B is in the middle. And ISR C get triggered first. Okay, when ISR C get triggered, I will enqueue function C. So if I look at my queue here, the first thing will be the function pointer to function C. Correct? And then what will I do? If after that, while I'm executing function C, okay, I execute a B get triggered. So when B get triggered, again it is ISR B, correct? So if I'm in the middle of function C is a code. The interrupt is to do the important stuff and put that pointer to the function inside the queue. So if now the function, the first element in the queue is the pointer to function C, when I do a dequeue, I will get function C. Correct? And then I will start to execute function C. And what is function C? Function C can be a long bunch of code here. Correct? And while I'm in the middle of function C, okay, ISR B get triggered. Okay, ISR B get triggered. When ISR B get triggered, what will happen? I will jump to ISR B and I will enqueue function B. Correct? Okay. Once I enqueue function B, can I execute function B? Can I? Cannot? Yes or no? How many say yes? How many say no? How many say it's almost a midterm question? Nobody. Sure, I don't want. I give you all option to choose question, also don't want. Okay, so your enqueuing is in the interrupt. But once your interrupt finish, I must still come back to here, correct? I must still come back to where I left off, which is my function C code. Correct? So I still cannot execute B yet, even though I say B is higher priority, correct? So even though I know that B is a higher priority interrupt, but since I'm in the middle of executing the function C, I cannot do B. So I still have to carry on with function C, and halfway, again towards the end, suddenly ISR B comes in. ISR A comes in, sorry. So when ISR A comes in, what will the event that will happen? I'll jump to ISR A. correct? Interrupt A trigger, I'll jump to ISR A, I will do what is important, and then I'll do enqueue function A. So this is where the queuing mechanism has a way to, or you can implement a way to focus on the priority. So if I know that A is higher priority than B, I can push function B here and make this function A to be the next one in the queue. And function B will come after that. So even though function B actually enqueued first, but before function B got a chance to run, function A already said I want to run. Okay? So I can push B to the back of the queue and function A take over. Okay? So that is the advantage of having this. Okay, so when you dequeue, you can dequeue based on priority. Okay, so that is the idea behind function queue scheduling. Okay, so it adds a bit more of an improvement, because when I have a lot of ISR, a lot of function pointer, I can choose the more important, more higher priority one, but it still never solve an important problem. The important problem is what? While I was executing function C, two other interrupt, which is higher priority, come in, but I still cannot go and complete the code for it. Correct? Okay, so that is an important issue that we are still haven't solved yet in this current approach. So we can enqueue a higher priority task to run after function C, but we cannot, in this current structure, stop function C and immediately jump to function A. So that part is still not settled yet. So this is the function queue scheduling. So you can enforce priorities in this scheme, okay, by managing the queues to ensure that the highest priority task will be the next one in the queue. So after all of that, now we finally reach the end goal, which is the real-time operating system. Okay, so you can see that there are alternatives. So don't necessarily think that I must always go to RTOS the moment my system gets complex. Okay, you can always try one of these other things, function queue scheduling or round robin with interrupt. One of these may also help and solve the problem. If all of this is not solving, or you think that your system is going to get more and more complex, then you go towards RTOS. And what is RTOS? RTOS is an inherent structure given to you to handle multiple tasks. Okay, the good part of RTOS is what? The good part of RTOS in this module is we need to understand the concept of how to use it. The actual internal sort of behavior and how to modify it, that is at higher level module. Okay, for this module, we are just understanding the concepts of RTOS and how we're going to apply it. Okay, so it's quite easy because we treat all the details as a black box. So I need to know the concept, okay, how semaphore works, how mutex works, how message passing works, okay, how queues work. I just understand the concept, and then I apply that concept in my design. Okay, so important thing is things like task scheduling. Okay, when I have so many tasks, okay, in a real-time system, I can have up to n to maybe 100, okay, to 1,000 tasks, no problem. Okay, you can have as many tasks as you want. Okay, so how do I handle all these tasks? How do I coordinate? When you have so many tasks, then there must also be ways for different tasks to coordinate with each other, send information to each other. And beyond that, the actual tasks, there are also other services. Things like, how do I manage the memory in my system? How do I deal with user interface, memory access, and so on? So the whole idea behind RTOS is to understand all of this concept. Okay, we are going to go into detail of RTOS in the next chapter. Okay, so this is just to give you a quick summary. So we'll have a 10 minutes break, and then we will start the next set of slides. Wow, all talk go home, right? All talk say go home. No, I don't disappear. So 10 minutes time, we'll start the next set of slides. Okay, so let's get started. Okay, so please settle down, settle down. Okay, so all the while we are still talking, talk too much until everybody bored already. Correct? This set of slides onwards, it gets more interesting. So we're going to go into actual RTOS details. Okay. So in this module, while we are learning some of the concepts of RTOS, we're also going to look at the analysis part in terms of timing, deadlines, and so on. Because we want to be sure that by using RTOS, I'm actually getting a better deal. Correct? So I want to be sure that after I put RTOS in the system, I'm actually able to get a better deal and sort of make sure that all my deadlines are met. Okay, so let's go on to task management. Okay, so these are important fundamental concepts that you need. Okay, what is the terminology that we use? What are the ways in which we call the terms such as process, task, and thread? Okay, we need to know how management is done. So when I have so many processes or so many tasks that are running, how do we manage them? Okay, processes, state, and life cycle. Okay, so this is important. Life cycle is very important because we need to know what are the states and the different state in which a process can be in. Okay, if you do not understand this, then when you are trying to analyze your code or try to design your code, you will not know how or why it is behaving that way. Okay, so this concept of state, processor state, is very important. Then what happens when I'm going to switch around? Okay, so processor context and context switching. Okay, and then towards the last part, we're going to talk about the case study or the application for your lab. Okay, so throughout this this module, plus you will see as well in other maybe resources, it is quite common to interpret and use the terms task and process quite interchangeably. Okay, so sometimes you see references, they call it a process, some they call it task in different textbooks or different resources, but in general, we look at it in the same light. Okay, so what is the definition of a process? Okay, we say a process is running when it's executing a program. Okay, example of a process is what? Okay, for let's say your mobile phone, you launch your media player to play a song. Okay, so that media player is a process. Okay, it is a process that will execute, and while it is executing, okay, it will consume resources from the system. You will have some input, it will have some output, okay, and you will execute code to fulfill the objective of the process. So that is a process. Again, you can also call it a task. Okay, it's up to you. In some of our references, we call it a process, and things that happen within the process, we call it a task. Okay, so we will again look through this terminology as we go along. The advantage of having a process model is the low-level mechanisms behind that are implemented are all within the RTOS. Okay, so again, this is very important. Like I said, what we are looking at is how I create all these threads, how are all these threads going to be managed, and how are they going to work together, synchronize, share data, and fulfill my objective. Okay, that is the main aim. So when you talk about process management, these are all the things that we need to be familiarized with, how we manage memory. Okay, then there's also the process control block that holds all the information related to a particular process. The process state, currently, what is my current state? That means, am I able to execute code, or I'm waiting for somebody to give me something? Okay, when I need to switch between the states, that is called context switching. Okay, how do I create a process and delete a process? Okay, and the concept of threads or tasks within the process. Okay, so this is the idea of a process in memory. Okay, so this is another way of looking at the interchangeable term of process and task. So here what they have done is they say this whole thing is a process. This whole thing is a process. And this process, what do you have? You have multiple tasks. Task 1, task 2, task 3, task 4. And each of these tasks, okay, if I look deeper, has some code that is written. So when you write a task, you're actually writing code. Okay, you're writing code to do some functionality and to achieve some functionality. And when you write some code, there will definitely be data. Okay, and you always will be using stack because you're going to be having function call. You need to push variable on the stack, retrieve variable. And you also have dynamic memory allocation, for example, malloc, where you use the heap. So you can imagine that in the past, when I just do my Arduino, right, when I do my Arduino sketch programming, for example, okay, when I compile my code, I only get this one thing, correct? Because I write it as a single while loop, correct? With all the task, function call, my array, usage, my malloc, everything inside one big while loop with all the functions and so on. So when I compile my code, the entire code comes inside this text section here. Correct? And all the variables I declare go into the data section. Okay? So I'm effectively, my whole microcontroller snapshot of my memory usage is this. Okay? But now, what am I doing? I'm not looking at it from such a big picture. I'm now breaking up the entire program into small subtasks. And each task is actually behaving like how my original code was going to behave. Okay, each task is now going to behave like how my original code is going to behave. So, task 1, task 2, task 3, task 4, and so on are each going to run as if they are the only ones running. Okay, of course there is the concept of sharing data and synchronization, but when you write a task, you do not care too much about anybody else. You focus on what you're supposed to do. Okay, so that is the whole idea of writing or breaking up your process into tasks. So coming back to this example, okay, so let's assume that my process now is my audio player. Okay, audio player on your phone. Okay, so now everybody launches your media player, audio player on your phone, alright? So now let's think of it in that context now. What are all the tasks that can be related to my audio player? What are all the things that I need to do or the system must be able to do while I'm playing music on my phone? The most basic task should be what? To be able to read from my memory, correct? And the most basic thing is I must be able to do a file access, correct, to my storage, whether it's SD card or local flash storage, and be able to retrieve this data, correct, this music file. Okay, so I need some memory or drive access. Correct? So one of the tasks to do this process must be able to do memory access. To go and read from my memory system and extract this data for me, this MP3 file. Okay? When I extract out this MP3 file, I cannot directly play an MP3 file, correct? I must do some processing. Correct? I must be able to decode it back to my normal PCM file that I can just output to my speaker or to my headphones, correct? Okay, so I also need to do some processing. Okay, so in task 2, maybe I can do signal processing. to process the raw data or the compressed data that I retrieve from the memory. Then once I get the data, another task could be to actually send it to my audio device. Correct? Again, don't think of this as sequential. It's not sequential, correct? Everything is running in parallel. Alright, because once I read from the memory, I do not need to process the whole thing at the same time. I can process 5 seconds at a time and then make sure that within the next 5 seconds, this data goes out. That's how you see buffering on your media player line, correct? Okay, so I can not necessarily have to do one task, then do the next task. I can all in parallel. As long as the end user, the person hearing the music, does not hear any interruption, does not hear a break, then I fulfill my real-time objective. Right? In this case, the whole real-time performance metric is the person hearing it must not hear any difference, must not hear that it's breaking up. So as long as he hears it as a continuous stream of music, then it's successful. So how you want to break it up is up to you. Whether I process 5 seconds at a time, 10 seconds at a time, that is up to you to decide. Okay? So of course, while all this is going on, I also must manage my user interface, correct? Because on your screen you have a button, right? The user can anytime say stop, fast forward, rewind, correct? And once the user interface task kicks in, then all the previous tasks also now need to go and readjust, correct? And you imagine right now I say I break up into 5-second buffer, then I doing this buffer, then I doing this, correct? And then suddenly the UI fella come in, say, hey, the song very boring the first part. Can I just forward until the last part? Correct? Then once the user interface come in, then everything else also must change, correct? Previously you are buffering from the start. Now you cannot buffer from the start, you have to jump. Correct? So all of this must now talk to each other, correct? All must talk to each other. So even though they are all running in parallel, there must still be a way for them to communicate. There must be a way for them to synchronize, correct? And get the output achieved. Okay? Now this whole idea, if I give it to you and say, run it as a single threaded program, no problem, we're all very happy. Correct? One loop, read all the data. One loop, decompress all the data. One loop, play all the data. User interface don't care. Correct? Or very simple, just pull on button. You either stop or you play. I don't want to give you anything else. Correct? Okay, so if I put it as a single threaded concept, it's very easy to think of it. Correct? I do step A, I do step B, I do step C, finish, repeat. Okay, so when you think of the problem single threaded, it seems very straightforward because I only doing one thing at a time. Okay, but once I break it up and say that everything must be able to run concurrently, it becomes a huge design problem. Alright, how do I break up this big task into different tasks that can still synchronize and achieve the output? Correct? So the most important thing, most students, when they learn about RTOS, they think that the coding part is difficult. No, the coding part is not difficult. The design of your code is the most difficult thing. Because if the design in your head is all messed up, then whatever code you write, no matter how wonderful you write, you will still not be able to achieve the objective because your original design of how many threads do I need, how do I pass the information around, how do I synchronize the information, that concept is wrong, then no amount of coding will save you. Correct? So the most challenging part in a real-time systems project is the design. Okay, how do I design the system to fulfill the objective using multiple threads? Using multiple threads. Okay, so now we are looking a bit more into details. So the first thing is the process control block. So what is the process control block? The process control block is a block that keeps track of all the information that is needed for that particular process. So coming back to this, if I write now that this process here is to do the memory access. So as far as I'm concerned, when I write this piece of task to do a memory access, okay, this memory access code will run as if it doesn't need to worry about anything else. Okay, but of course we know that, or we will see that it doesn't necessarily have to run to completion. It can also be forced to give up to allow other tasks to run. And that is the whole idea of having an operating system. So while I'm running this memory access code, I'm executing some code. So this code, if I look at the text, let's say I look at the whole code here. Okay, so this whole code here, again, within the task itself, I may have a lot of lines of code. And I also have all my data, so I have all my memory variables, okay, inside here. And while I'm executing this particular task, before I finish, I may be forced to give up and let another task run. Okay, it could be part of your design, or it could happen because really someone else is more important. Correct? So if my memory access, okay, so if I'm supposed to read, and maybe you're playing a very big file, okay, that goes into maybe 128 megabyte. Okay, so instead of accessing all of that into your memory, which is going to take up too much of space, correct? So you say I just access 1 megabyte first. Okay, so when 1 megabyte is finished, okay, I will get to give up and let another task run. Okay, but when I give up, when I come back here again to resume, I must know where I left off, correct? I must know where I left off. My code must still be retaining all the information that I had before another task took over. So all of that information in terms of my registers, my memory, all of that is inside your process control block. So your process control block is like a snapshot of your task at any time. Okay, it gives you all the information of how much memory you have used, how big is your task that you've written, okay, what are all the register values that you are currently having inside your system, and any open files that you have. Okay, each process or each task has its own process control block. Okay, and it looks again something like this. So there's a pointer to the process, there is a process ID. Your program counter is because you are keeping track. Correct? The program counter is basically what? Your register that points to the next instruction to execute. Correct? So that program counter plus CPU register. So you have learned about microprocessors and your internal registers. Correct? Okay? So no matter how much we code, eventually it still gets translated down to your register level access. Correct? Which are the registers? Register R0 to R7, R8 to R15, and so on. Okay? Then your memory plus your files. So all of this gives you a snapshot. Okay? At this point of time, this was what this particular task was doing. Okay? So again, this is important. Why? Because when I'm switching, later I'll talk about the switching part. This process control block gives me the information that I need so that I know that at this point of time, I was forced to give up. Okay, give up CPU. Okay, when I return, I must be able to carry on exactly from where I left off. Same concept as your function call. Correct? When you are doing a function call, you have to push. When you jump to a function, when you finish the function, you return back, you also expect to carry on exactly where you left off. Same concept for interrupt. When you're executing a main code and the interrupt happens, you jump to the interrupt service routine. Correct? You finish everything and then you jump back. You also expect that when I jump back, I carry on from exactly where I left off. Okay, the same thing. But in this case, it is a lot more information that you need to save. Okay, why? Again, your concept must change. Right? Your concept is that each task is as if it is its own program by itself. Each task is like a mini computer program by itself. Okay, in the past you write one big program. Okay, now you are writing small mini programs, but each program is by itself. Okay, so this comes to a very important thing called process state. Okay, so what is a process state? Okay, so there are a few, this terminology again, some textbooks they have slightly different names, but the whole idea is the same. Okay, so if you refer to online resources to go and read up, the terms that they use may be slightly different. Okay, created, okay, some of them don't have created state. Okay, so again, some of these states you will see that they are not existent in some other OS. Okay, because some OS has specific way in which they do certain things. So created is the original state that you're in immediately after creation. Running is when you're executing. Blocked is when you're waiting. Again, the next few slides we got more detail. Ready is when you are waiting to be assigned. And terminated is when you finish execution. Okay, let's look at it from this point of view. Okay, so this shows you a diagram or a process state. Okay, before I go into this, let's look at each state one at a time, and then we understand how to relate back. Okay, let's look at the first one, which is created state. When you say a state has been created, or a process or a task has been created, what does it mean? It means it now has a process control block. Okay, so when I create a task, I'm creating now a mini computer program. I think of it that way. Okay, I'm creating a new mini computer program that can now run by itself. So to run by itself, you must have a copy of the program. You must have its own PCB, program control block, to keep track of all its internal registers, its memory, okay, where it's executing, and so on. A process can only be created if there exists minimum bare resources to support it. Okay, so this is important because when I create a process, that means now, again, the idea is what? A process is like a mini program. If I want to load my program onto my Arduino board, I must make sure there is enough memory on it, correct? Okay, so if I write a program that is so big, and you try to compile for the Arduino Uno, and it's too big, they will flash out an error there, compile error. Okay, they will say that your program is too big to fit onto the Arduino Uno board. Okay, so the same thing over here. When I want to create a process, I need to specify how much memory I want for this process. Okay, for this task. So if now I'm creating a task to do the signal processing, correct? And maybe the signal processing I need to do all my Fourier transform and all this transform, which takes up a lot of memory. Okay, so if I try to create and the system says I don't have enough memory, then I need to do something about it, correct? Then I won't be able to create. So a new process can only be created if I have enough resources to support it. Okay, it does not yet compete with the CPU for other processes at this point. Okay, the next state is what? This is called the ready state. Okay, when you are in a ready state, what does that mean? When I say my task is ready, it means it has all the resources that it needs to execute. It has all the resources it needs to start executing. Okay? And it will now start to compete with the CPU, so compete with other processors to gain access to the CPU to execute. Okay, so when I say the task T1 is in a ready state, okay, that means it is now ready to execute code. That means whatever code that I've written for task 1 can now be executed. Okay, but again, we are only thinking of the single processor idea here, alright? We're not talking about multiprocessor, multi-core architecture here. So in a single processor environment, I have so many tasks, correct? Okay? So if task 1 is ready, then I have another task 2 also ready. Okay? Then I have another task 3 also ready. So I can have a lot of tasks in my system that are ready. Okay? Again, ready means what? That means I have everything that I need and I cannot execute code. But I only have one CPU, correct? Ultimately, no matter what you write, like I said, it comes down to the processor. Architecture means only one CPU, one line of code at a time, correct? So, since I have only one CPU, only one process or one task can run at any time. So, out of these 3, task 1 and task 2 and task 3, only one of it can start to run, even though all may be ready. Okay? So, if task 2 is selected, to run, then the other tasks will still be ready. So if there is no processor available, I will still be ready. Don't say wait. A lot of students will say, okay, that means this task is waiting. No, it's not waiting. Okay? Don't use the wrong term, because in OS, the term means a lot. The state that you use, the terminology you use says a lot. Okay, so this is called a ready state. Ready state means I have everything, but I cannot run because the CPU is busy handling another process or another task. Okay, so that is what you mean by ready state. Okay, so there is an OS function that will execute to go from created to ready state. Okay, this one, no need to worry. This part, when you do the lab part, you will understand. Okay, so the OS should ensure that all actively competing tasks are able to have enough time to take over the CPU and run. Okay, so schedulability, you'll look into more detail later on in other slides. Okay, running. Running is out of the tasks that are in the ready state, one will be selected to go into a run state or running state. So when I say that that particular task has been selected to run, that means it is executing code. Basically, it means it is executing code. Okay, so who makes this decision? Who makes this decision? Because I can have so many tasks. I have so many tasks in my system, and everybody says I want to run. Okay, everybody says I want to run. So who will be selected? That is the job of the scheduler. Okay, so this scheduler, which is again in the OS, is like the big manager. Okay, he looks at everybody and he makes a decision. Of course, there are rules, okay, that he has to follow. The scheduler has to follow to make the decision on which task will be selected. Okay, but it's the scheduler's responsibility to decide who should run. You do not control. The programmer does not control. Okay, that's why I said the programmer mindset must switch such that every task is a mini program by itself. I must put in the necessary logic and the safeguard to ensure that this task that I write will run when the data is available. And if it's supposed to synchronize with some other task, I also need to put that in my code. Okay? You do not explicitly call a task to run. That is the job of the OS. Okay? Now the thing is, when I am running, I cannot run forever. You imagine this situation where task 2 run. And task 2 run happily. I have CPU to myself. Keep running. Go back. Then keep running. Correct? Okay? So if task 2 does that, then the whole system fails. Correct? If task 2 does that, then it's like the whole system fails, because it's going to hog the CPU indefinitely. And all the other tasks will never get a chance to execute. Okay? So in order for you to do that, in order for you to prevent that, okay, there is a mechanism where from running state, you can go back to ready state. Okay, so there's a few different possible ways in which your state can change. This is one possible state. From running, I go back to ready. When does this happen? When does this happen? This happens either through preemption or through yield. So again, these are two different terms. What is preemption? Preemption means what? Somebody more important wants to take over. So again, more important generally means higher priority. Okay, so when I create a task, the priority is one of the parameters I must specify to say how important this is compared to the rest of the tasks in my system. Okay? So one way in which while I'm running, I may be preempted. So if I look at this situation, if I say task 1, task 2, task 3, and out of the 3 tasks that are ready, task 2 is running, means from these 3 tasks, task 2 is the highest priority. Okay? Either task 2 is the highest priority or the task 2 was the first one to become ready. Okay, so that is the situation. But when task 2 is running, at any time here, it can get preempted if there is a task 4 that is even higher priority than task 2. Okay? If task 4, there's another task 4 that is higher priority than task 2, then it will be known as preemption. The other alternative is called yield. Yield means what? You voluntarily give up the CPU. Voluntarily give up the CPU so that you allow other people to run. Okay, so there is 2 possible scenarios here. One is you're running and somebody else more important wants attention. So your scheduler will put your task on hold, switch you back to ready, and let the other tasks run. The other one is yield, where you voluntarily give up the CPU to allow other tasks to run. So important thing you must remember here is what? If a situation where task 4 comes in, okay, and task 4 is higher priority, okay, so if I say this is 1, 2, 3, 4 priority, and task 4 is now running. So when task 4 is now running, what is the state of task 2? When task 4 is now running, because task 2 is preempted, task 2 state is now what? Ready. So from run, we go back to ready. Correct? So again, in ready means what? That means actually task 2 is still having everything it needs to run. So task 2 is still willing to execute. So ready state means what? I have everything I need to run. But whether I get a chance to run or not is the scheduler's responsibility. Okay, so the scheduler will come in and see now task 4 is available and it wants to run. So task 2 will be preempted and task 4 will run. So task 2 will go from run to ready. Okay, so this whole process will carry on. So later on, then task 2 will get a chance to run. Okay, the other state is called block state. In some books, they will call it pending state. Okay, it's the same idea. When do you say you are in a pending state? When you have to wait for something. Okay, that means you are maybe waiting for some data to come in on the serial port. Okay, if the data never come, then I got nothing to do. Correct? So it's a block state. Or I'm waiting to synchronize with other processes. That means I'm waiting for task 5 to send me some message. So if task 5 haven't sent me, then I wait. Okay? Or I want to communicate with other processes. Okay, I want to send some information over, so I wait first. When I'm in a block state, I do not compete for CPU. Okay? In a ready state, I am competing with the CPU. In a ready state, I'm competing with other processors for CPU time. But in a block state, I do not compete. Okay, that means I am not yet ready to run. I'm not yet ready to run because something is missing. I'm waiting for somebody. Okay, you're waiting for some event to happen, some information to come through, then I can run. But until then, I do not want to compete for CPU time. Okay, so that is called a block state. Okay, so this is also another important thing you must understand. If I'm in task 4 now, okay? Let's say this task 1. Okay, I run, and over here, I decide to wait for a resource, for example. So all the while here, I am running. Okay, so So before that, you were in the ready state first. Okay, and then you run. Okay, and some point of time, you are waiting for a resource. So when you're waiting for a resource, you get blocked. Okay, why you are blocked? Because you're waiting for some resource. So in your code that you write, you would have written that maybe, okay, wait for data to come in from serial port, or wait for message to be received through my encoder. Okay, something, some event, or wait for interrupt to happen, something. So you're waiting for the event. So until that event happens, you're going to be in a block state. So you do not know how long. And suddenly that event occurs here. The resource is available. The resource is available. Then what happened? I was waiting for data to come in, and suddenly now data come in. Can I run? Can I run? I cannot. Because somebody else could be running. Correct? The moment I gave out the CPU, the scheduler would have assigned somebody else to take over the CPU, correct? So during this block state, we do not know who was running. Somebody could be running. So even though I may get my resource, I still cannot straight away run. I must first switch to my ready state. Again, ready means what? I have everything I need. So once I have everything I need, then the scheduler will decide when is your time to run. Okay? So once I'm in the ready state, okay, then it is the scheduler's responsibility to decide if now task 2 should be allowed to run. If this task 1 should be allowed to run. Okay? Again, it will make decision based on priorities of all the tasks that are currently in the system. Waiting to have a chance. Okay, so once you are blocked, you will transition to ready. Then from ready, once the scheduler make a decision, then you can go to run. Okay, so that is the state transition. So you must be very clear on the state transition. Okay. Sorry. Okay, terminated is when you no longer need a task. Okay, so sometimes you create a task for a particular purpose only. Okay, and once you finish that task, you may no longer need it in the system at all. Okay, so the whole task can be deleted. Okay, so when you delete the task, you no longer have the ability to execute it. Okay, again, we rarely need to do this. In most cases, we will create only the tasks that we need and we will manage with that. Okay, so let's come back to this diagram for a while. Huh? So you can see that the very first time I create a task, okay, I will go into a ready state. Okay. Again, there are a lot of tasks that can be ready at the same time. Of all the tasks that are currently in the ready state, okay, all the tasks that are in the ready state, one of it will switch to running. The rest of it will still be in the ready state. Okay? And when I switch to running, okay, what will happen? I will run until when? Until a point of time where I may switch back to ready state, either by preemption or by yield, or I may go into a block state because I am waiting for some event, I'm waiting for some data to come in, okay? And if I go back to ready state because of preemption or yield, then from ready I can go back to run again when the scheduler makes a decision. If I go to a block state because I was waiting for some resource or something, then after that resource is available, I will go to ready state. Then from ready state, I can go to run state. So you see the flow? So that is the general idea of all the different states, okay, in the transition. Can? Okay, so I will stop here for today. Okay, so this week, Wednesday, you will start your lab 2. Okay, the material is already there. You can go through with your Arduino board. So remember that this week's lab and next week's lab is the same lab session. End of next week, you need to demo. And by the end of next Friday, you need to submit your report. Okay, thank you. See you all next week.